Hello, my name is Marshall Monsivais, and I'll be discussing my research project, Incorporating Spatial-Temporal Controls within a Generic IoT Model. I want to thank my mentor, Dr. Mustafa Al-Lail, for his help during this project. Before we go into the project too much, I would like to go over an overview of what we'll be discussing here. So I'll go ahead and give you an introduction to the problem we're facing. Then I'll discuss the objective for this project and contributions I've made for it. After which I'll go ahead and I'll talk about what spatial temporal access controls are and how they're used here. I'll give an overview of IoT, and then I'll go ahead and discuss the proposed model in terms of the different layers that compose it. After which I'll go ahead and discuss the sequence diagram of the IoT model and how we might see modification of an IoT device in action work in terms of communication. After that, I'll go ahead and discuss the implementation of the IoT model that we created for this system and the challenges that went into creating it. After which, I'll go ahead and discuss experiment design for this project and future work we'll be seeing. So just as an introduction, we've seen a great big uptick in the usage of Internet of Things devices, IoT devices, in both consumer and industrial settings. So we're seeing all sorts of virtual assistant security systems, industrial equipment, all these things that are using the internet to try and supplement their computational capacity. Many of these devices, however, don't check the time and location of access requests, leaving them open to security vulnerabilities related to accessing information in unauthorized locations or at unauthorized times. So our objective for this project is we wanted to design an IoT model that incorporates spatial temporal access control when a person wants to try modifying a device or accessing information from a device. We wanted to also go ahead and create a software implementation of this model and then write a technical paper describing the IoT model and the implementation. So our current contributions is we've designed an IoT architecture based on a general model proposed in Access Control Models for Cloud-Enabled Internet of Things, Proposed Architecture and Research Agenda. And we've also gone ahead and we've designed a simple prototype model that demonstrates the functionality of this model in action. So before we get into things, let's discuss what spatial temporal access really is in this context. So when we're talking about access control, we're talking about whether or not a person should be allowed to receive access to resources online. So a person asks for maybe access to medical records, uh, and they have to receive access before they can actually, modify those records, read them, what have you. So in terms of access control here, we want to restrict based on spatial controls and temporal controls. So a person needs to be in an approved location in order to have access to files uh, or the ability to modify things. Uh, and they also have to be within the correct time to access those files. So if they're in this particular example, if a person's in a hospital, they would be allowed to access resources. And if they're accessing during the daytime, they would also be able to access resources. But if they were at home or if they're trying to access during nighttime when they're not allowed, in both cases they would fail. And these two restrictions, the spatial and temporal restrictions, they work together. So they both have to be correct at the same time in order for a person to be able to access resources. And so for this particular project, we want to focus on IoT devices. So what are IoT devices? So IoT devices are devices uh, that use cloud computing in order to supplement their own hardware. So they're fairly weak in terms of the actual hardware stored on the device, but by using cloud computing, they can help bolster their actual computational ability and their storage capacity. So for IoT, there's not really an all-encompassing model for IoT devices. There's many different variations on how people would want to implement these systems. But for this project, we've gone ahead and we've used this particular model shown to the right that's composed of four distinct layers. We have an object layer that represents the physical objects in the system, the actual devices. We have a virtual object layer that is an abstraction of physical objects. We have a cloud services layer that's split into two halves. One half is stores the data and performs calculations on things, and we have the other half which performs access control decisions. So it decides whether or not a person would have access to this system or certain aspects of the system. And then we have the application layer, which is the user application that's used for remote interaction with objects. So the first layer we'll talk about the IoT device, the object layer. So objects are essentially just IoT devices within the system. They have the capacity to influence the world around them and take in information from the world around them using actuators and sensors. So as we said before, these objects have a limited computational power and memory, but they do have the ability to maybe influence the world via maybe speakers or small motors. Uh, and they can take in information through their sensors. So they don't actually have the capacity to store this information long term. So they go ahead and they distribute that to virtual objects in the system that are connected to them. People can also command them remotely to try and get them to perform certain actions or alter how they're receiving data. Uh, and just an additional consideration we've made here is if objects are lightweight enough to be movable, then we think there should be GPS functionality just to ensure that these objects aren't misplaced by somebody and accessed during inappropriate times or locations. If it's a particularly heavy object or some sort of object that's rooted in some fashion, then we don't think that would be a necessary thing to implement in this in such an object, just because we want to limit uh, how people are interacting with this object and accessing resources. For a virtual object server, we would go ahead and see that they're abstractions of actual objects. They basically just contain information about the status of the object, information collected from the object, and they'll go ahead and they'll make decisions as to whether or not they need to store this long term or not. So there might be cases also where there's multiple virtual object servers that are working together, uh, or there might just be one virtual object server that encompasses all possible objects. It depends on the particular setup, uh, but in any case, regardless of whether there's only one virtual object server or multiple virtual object servers representing different types of objects, we see that data is only stored here temporarily for all of them. And what information is sent to the resource server for long-term storage has to be determined only if certain conditions are met, essentially. So if there's a certain criteria for this virtual object server to send information, it'll go ahead and send it at that point. And this information might be changed depending on the resource server or maybe some certain criteria uh, in terms of it's seen something in a sensor or heard some sort of keyword, something like that. And it'll go ahead and send information where it otherwise wouldn't. Going into the cloud services layer, we have again the two halves. The first half is the resource server. And so this resource server, it stores collected information for the long term, and it'll forward requests to modify devices in the system to the virtual object server. Complex calculations also can occur here, depending on exactly what kind of device might be needing them. So if you see something like Alexa, Alexa can't process voice commands in itself. It needs some third-party application to do that. So we would have to rely on a resource server sort of thing to process that information and send a response back. And other types of APIs might be fulfill similar roles for other types of devices. It depends on the situation. Uh, but in any case, in order to actually modify any data that's being obtained by the system or uh, modify devices in the system, a person needs to get authorization first. So the resource server isn't just going to let people modify things willy-nilly. It needs some sort of authorization first by the authorization server. And lastly, we can see that changes are propagated using topics to try and distribute information to subscribed entities. So topics in terms of a pub sub format are they have I should say they have the ability to vary easily distribute information amongst entities that are subscribed to it. So, just as an example, if there's a resource server that's subscribed to a particular topic, if a virtual object server publishes information to that topic, then since the resource server is subscribed to it, it'll automatically receive information that was pushed into it by the virtual object server. So it's just a quick way of communication that allows for information to be distributed to anything that's subscribed to it. So the second layer we'd want to discuss is the authorization server, or the second half of the cloud services layer we want to discuss. So the authorization server determines whether or not users should be granted access to data or device modification privileges. So based on the ST zone of a person, that is the combination of the time that they're accessing or requesting access and the location in which they're requesting access. Uh, it'll look at that and it'll look at other factors like their role in the system, what kind of activity they're trying to do, things like that, different factors. It'll go ahead and make a decision as to whether or not a person should be able to actually uh, get the access to do the thing they want to do within the system. And so if access is granted, it'll go ahead and send an authorization token back to the resource server, letting it know that, okay, this person is allowed to make the modifications they want to make, or read the information they'd like to read. So lastly, we have the application layer here. And so the application is just for the user to be able to access the IoT devices remotely and access information regarding those devices remotely. User requests, it contains things like their credentials, their SD zone data, which is again their location, the time of access, what activity they want to do in the system, uh, what device do they want to access maybe. So things like that are sent. And so they can use this application in order to, perform those functions, to modify devices, to read information, things like that. So here we have a sequence diagram describing the process of modifying a device within the system. So what a sequence diagram is it's just showing the chain of communication between the different components in the system in order to accomplish a task. So here we see a person making a request to modify a device. So they're going to go ahead, they're going to log into the resource server, they're going to go ahead and request a resource from it. That resource server, it's going to then go ahead and talk to the authorization server and ask, hey, is this person supposed to actually receive access to these, to modify this device in this scenario? And so if it says yes, the person will get an authorization token back from the resource server and they'll be able to actually modify the device. And so when they want to modify that device, it's going to send a message over to the virtual object server saying, hey, we want to modify, let's say, device one. And so in this case, it'll go ahead and send that message to device one that, hey, we need to make this so-and-so modification. Device one will make that modification, and then it'll return a response saying its current state and the fact that, it made the modification. And so the user will eventually be passed that information that, yes, this modification has been made. Maybe they'd want to make other modifications. So next we can see the scenario where maybe they do have access, but uh, they leave particularly a particular location that was approved, and they go to a different location that's not approved, or maybe they were accessing during a certain time period, but now it's past that time period. It'll go ahead and revoke access if they no longer have, or if they're no longer in an approved time and location. And again, if a person was never granted access in the first place, they simply don't have access to the ability to modify the device in the first place. So we've gone ahead, we've created an implementation of the IoT model we've created uh, based on it displays the functionality we saw in slide 11 very well. Uh, So what we have here on the right, we have a person, they want to modify an IoT device. They go ahead and they request the ability to modify it. And they have now been granted access to modify it. So if they go ahead and they switch it on, they can go ahead and toggle on the device. So this is just representing, the actual process of it. There's what's shown here is only the application layer, but there's also different servers going on in the background communicating with each other, granting access, uh, asking for resources, asking for modifications to be made to IoT device. In particular, we created a dummy IoT device. Rather than using an actual physical device, we have a virtual device that sends back sensor data. It sends back the device's current state, the device's ID, things like that to the resource server. Uh, in terms of challenges in actually creating this, we needed to create a generic IoT model where one really doesn't exist. Again, there's not an all-encompassing model for IoT devices. There's just too much variation in terms of the different types of devices, the different types of systems. Uh, so there's a lot of variation in how people try to implement these systems in the world. But we went ahead, we went with a model that's reasonably encompassing of the different aspects of the IoT system. Another problem we faced was communication between components. We had to design asynchronous communication between many of the components, in particular between the virtual object server and the things it's connected to, the IoT device and the resource server. Uh, we had to integrate different cryptographic tools in the communication protocol in order to ensure, these communications are secure. In particular, with the IoT device communication with the virtual object server, we have a less computationally intensive algorithm going on there rather than RSA encryption, which is occurring elsewhere in the model. Uh, and lastly, we also had time constraints in developing the IoT implementation. We had to consider what features need to be prioritized in terms of development, what best represents the actual communication protocols we're trying to show in this model, in this implementation. So those are things we had to consider when we were working on this. So going forward, we want to run experiments regarding this model. We've considered what we could do, and we're thinking on beginning to conduct tests regarding the overall latency of the system. So basically just how quickly are commands distributed from the user to the IoT device, uh, like how much time does it take for access to be granted in the system? How long does it take to modify the IoT device once access has been granted? How long overall does it take for modifications to be made and for the user to be made aware that those modifications have been made? Those different aspects are things we'd like to investigate just to see how long these things take within our system. So just as a conclusion, again, after researching a generic model for an IoT system, we developed a new architecture, developed to incorporate time and location when making access control decisions. This model contains those four layers we talked about earlier: the object layer, the virtual object layer, cloud services layer, and the application layer. We created a simple implementation to demonstrate the properties of this system, demonstrating the chain of events from a user requesting to modify an IoT device to that device being modified. And it shows the different communications between the various components in the system and shows how the IoT device can continuously update the resource server with sensor data, its current state, things like that for long-term storage. And going forward, so we're going to go ahead and continue writing a research paper of the model, discussing the findings we've made and the work that we've done here. And we like to go ahead and again conduct different experiments to test the functionality of the IoT implementation and the different latency statistics that we'd like to look at to see how effective it is. And here are our references. Thank you.